I'm Paul Dvorak, editor of Windpower Engineering magazine. We're here at Windpower 2011, AWEA's show in Anaheim, and I'm with Nick Harper. He's the product manager for an unusual product for Moog. Nick, you got a device that'll detect ice now in an unusual way, a little bit more efficiently, I understand, from previous methods. Can you tell us about it?
I can, Paul, yes. The system depends on using optical sensors, and that's the key issue to the whole technology. We're using optical sensors because any other sort of sensors invariably has metal components in it, and these metal components would be suspect to lightning strike and possibly to EMI interference. So we do the whole thing using optical sensors. As you can see here, we have a sample set of sensors there, which we take and put fiberglass or composite around these optical fiber, and we attach those to the root of the blades. And the signal then is taken from the root of the blade. It goes back into the hub where we mount our optical interrogator, and that takes the raw data, processes it, and provides it to the next set of equipment, which we call our rotor monitoring system. And it's the rotor monitoring system that does all the intelligent part of the interpretation of the data.
Okay, so essentially, as I understand it, the blade acquires mass as ice accumulates on it.
That's right. So as the turbine is rotating, ice accretes normally onto the leading edge of the blade. That effectively changes the mass of the blade. So as the turbine is rotating, we can detect that. We can see that build up. But the beautiful thing about the system, there's no point having a system that just works dynamically and then closes it down. When the system is stopped and stationary, it still goes on working, because then instead of working in the time domain, we go into the frequency domain, and we now look at the vibration signature, the vibration characteristics of the turbine, of the blade. And then as the ice then melts from that, that vibration component will change and revert back to what it was originally, and then we can make the decision, the turbine effectively can make its own decision whether it starts up or not.
Okay. All right, now there's equipment in the blade and there's some equipment in the hub.
That's correct.
Okay.
Can we walk this way?
Yes.
This is the equipment that we have mounted in the hub. This is our optical interrogator. You can see the box there. It's a 3-channel device, which is perfect for wind energy because, as obviously, we've got 3 blades, so we have one optical cable coming in from each blade. The data comes out in serial form and goes into our rotor monitoring system. You can see that box there.
That's off to the side.
That's off to the side there, exactly. And that's where inside there it has its own microprocessor, and embedded in that microprocessor we have all the facilities to run deeper algorithms to extract from the raw data all these clever components about the integrity of the rotor and the ice build-up on the blades.
And can the system start the turbine earlier than in other ice detection devices?
Well, I never like to talk about other ice detection devices. All I know is that our system does do that, yes. As I said earlier on, when the system is stopped, it's now looking at the vibration signature of the blade. As ice builds up in the blade, the vibration characteristics go down, and as it comes back up again as the ice melts, yes, it can then make the decision to start the turbine. This is really useful for turbine operators, because obviously a parked turbine is bad news for them, but a parked turbine means they're losing revenue. So the earlier they can start it up, the better it is. In some systems, it's traditional to have to send people out to the site to go and see if there's ice off the turbine. Well, that's obviously hopeless.
Oh, this is a significant technical development.
Absolutely. And as technology, that really does work.
Thank you very much, Nick.
My pleasure.